Bobby Fazio.
All right, welcome back. Driver interviews with Bobby Fazio. I am Bobby Fazio. Today is Tuesday, January 17th, 2023. It's the Tuesday tell-all, but you know how we do. Once a month, we do a tech segment where you stock and super stock racers out there can learn and apply technology, new technology to your rides. Squeeze out a couple extra horsepower. That's what we're all in it for, right? Performance-based class. We got to be ready for those heads-up races. So who better than to have our guest today, Lake Speed, the brainchild, the tribologist, the friction master.
Exactly.
The friction master, come on and talk to us again. Now, you all may have seen a tech episode that we did on the Class Racing Today podcast a year ago, and we will include a link to that podcast so you can rewatch that episode and learn from Lake in that episode and learn from Lake again today in this episode. So, Lake Speed Jr., how you doing, sir?
I'm fantastic. Oh, by the way, January 17th, shout out to my dad. Happy birthday, Dad. 74 years old.
Happy birthday, Lake Speed Sr., 74 years young. How about that?
Yep. He's still out there getting it, too. He's out there still going fast, go-karting and everything. And in fact, I just got back from the Engine Performance Expo. So we did that over near Bristol, Tennessee last week. And really, if you're into tech and you want to have your mind melted, just go over, when you get a chance. So finish this episode first. So later, go to YouTube and just type in Engine Performance Expo. Go to the channel. We did 2 days, 8.5 hours live stream for 2 days, 50 different tech segments. We had John Kazi, we had John Callies, Scooter Brothers, Mark Cronquist, Keith Dorton, Greg and Aaron Stanfield, Steve Morris, Dennis Borum from Pro Motor, Jason Line. Yeah, we had Jason Line in studio, on set, picking his brain, all that kind of stuff. And we covered a bunch of different things with the Engine Performance Expo. We've got, interviews. We've got these roundtable discussions. We've got a lot of recorded sessions. Ben Strader, Billy Godbold. I mean, it's really the all-stars of engine building are there. If you watch it, you are going to learn something. And, Bobby, one of the funny things is, this year we had we'll call it our put up or shut up moment. We do all this talking about, tribology, oils, fuels, rings, honing and all this. We came across a project this year, going back to my dad, that there's a guy named Mitchell Stapleton. He's got a channel called Stapleton 42, and he's been doing this racing history deep dive this past year. And he came and went to my dad's shop, and we did a walkthrough, and Mitchell sees these engines sitting on the floor, and he's like, "What are those?" And Dad's like, "Those are some old Bush 9-to-1 motors that I bought to go do vintage road racing with." There's his friend Bob Cronin, CRD Engines, who actually passed away several years ago. But Bob was one of the Fram spark plug guys, Champion spark plug guys, and got into doing engine building, was a great engine builder, won lots of road racing stuff. Really great guy. He freshened the engines up for Dad, and Dad used them for vintage road racing after he had retired from NASCAR. Well, the engines have been sitting on the floor for 18 years. And Mitch was like, "What are y'all going to do with those things?" Said, "Well, I don't know." And Mitch was like, "You think you still drive a car?" Dad's like, "No, I can drive a race car." It's like, I'll tell you what. Let's take that last motor you ran at Daytona 18 years ago. We'll freshen it up. put it back in the car and let Dad go back to the racetrack. So that's what we're going to do. Sometime this year, we're going to put that engine that we just got freshened up. We're going to put it back in the car. Dad's going to go up to Virginia International Raceway. It's a big, giant, beautiful road course, and go run. We actually said, hey, you can go to Rockingham because they've got the track just repaved. He's like, I don't want to go somewhere small. I want to go somewhere that's got big, long straightaway so I can go fast. Okay. He wants to go through all the gears, right?
Yeah.
Which is good for him. So anyway, a little backstory. So we decided we were going to do this program. So Dennis at Pro Motor over here in Mooresville, that's who built engines for Dad at the very end of his career. So we took that engine that had run at Daytona in 2004 and won the race, the vintage race down there, put it in the dyno. We ran it. It made 477 horsepower.
And there was a lot of disappointment on people's faces.
Oh, very much so. Because
we will include a link to that video, by the way. You can click the link.
Yeah, Dad had thought it made like 720 or something. And we found some dyno sheets after the fact that said, yeah, when it was new, it made 720. But then, fortunately, I'm going to jump a little bit ahead. We'll jump around in the time frame here. That when we had Greg Anderson, yeah, you heard that right. Greg Anderson was honing the block for the refresh for us because we decided to go all in, right? This thing was down 477. We had to bring in all of our friends. We had to make a complete all-star effort to try to get this thing revived because if you're down that far, there's kind of two things. Well, your threshold is pretty low, so it's going to be, it should be able to go up. But the problem is you got a pretty high mountain to climb to get back into the 700, right? So we got Greg to hone the block. I'm over there at Greg's, and he's honing the block. And there's a video for that you can watch of how to hone a block. Greg Anderson will show you how to hone a block.
We'll include that link too.
Well, Jason Line was there. And we started talking about this stuff. And Jason's like, well, what dyno was it? I said, Superflow 901. He said, 2002? I'm like, yep. He said, I can tell you what happened. You got the dyno sheets? Yeah. So we grabbed the dyno sheets. And Jason goes through and shows where that 720 horsepower was mythical. That wasn't real. And it's because the older dynos, there's a strain gauge that measures the torque. Because horsepower is calculated, torque's what's measured. The strain gauge back in the early models of those dynos was not temperature compensating. So the longer you ran it, the hotter it got, the more it expanded. And if you weren't hanging the weights on it and recalibrating it after the 20th dyno pull, it wasn't telling you the truth.
Oh, okay.
Which is why people said, oh, that motor made a ton of power on the dyno, but it wouldn't go down the racetrack. We've all heard that, right, Bobby?
Right, absolutely.
Well, like Jason said, there's no way. If it makes more power, it will go faster. So what was going on? Well, what was happening is our calibration on the dyno was off because it wasn't compensating for temperature.
Right.
Well, all the new dynos all have a thermocouple on the strain gauge now, and they're compensating for the temperature of it.
Okay.
So that's one of the advancements of the latest technology. So we go back and we look at that history, look at all the dyno runs and look at all the notes. We're like, oh, this thing really made about 680, 690, right? Give or take, right?
All right.
We don't know what it really was, but when you had the air fuel ratio right, it's somewhere probably between, we'll call it 670 and 690 is probably the real number of what it really made when it was all tuned up. Okay. So it dynoed it, we'll call it 480, but it was probably really about 680. So it was 200 horsepower off.
Yeah.
We're like, tore the engine down. We couldn't find anything wrong with it other than two cylinders that had some micro welding in the top ring, and there was some rust in the bores. And we're like, well, here's the other thing. We started saying, well, hang on. This math doesn't add up. even if it was a 700 horsepower engine and you divide it by 8, that's not 100 horsepower per cylinder. So what's going on? Common plenum manifold. So in the Engine Performance Expo, we do a segment with Ben Strader where we had in-cylinder combustion analysis. So we've got a pressure transducer in all 8 cylinders, so you can actually see the entire pump cycle, all 4 cycles. You can see the compression, you can see the combustion, you can see the exhaust, you can see the intake, you see it all. You see all the pressure of all the cylinders. And you can see it on all 8 cylinders. And to give you an idea of how much crosstalk there is between cylinders in the manifold, we had small diameter long tube headers on one side of the engine, and we had big diameter short tube headers on the other side of the engine, and we could swap them back all around and you could see how they all change. In fact, the engine actually made the most power with the short tube, big diameter short tube headers on the driver's side of the engine, and the small diameter long tube headers on the passenger side of the engine.
Wow. Interesting. Right. Staggering the header sizes. I like this.
I mean, we just started throwing crap at it. We were like, this is kind of crazy because we talk about these engines being a V8. We're, it's an engine. No. When you have a common plenum manifold, you have 8 single cylinder engines all living in the same house. And if you got kids or siblings, you already know where I'm going with this, right? Not everyone gets along. Not everyone cleans the bathroom after they left, right? So from cycle to cycle, you can see these variations, and there's a really famous video that John Kazi did from AETC, I think about maybe 6 or 7 or so years ago, where he put his finger in the manifold, in one of the runners of the manifold. And he said it almost blew it off because he thinks, okay, put your finger in like this because it's going to be going down, right?
Yeah.
No, he said the pulses going back up toward the carburetor were just as strong as the ones down. And if he rotated his finger sideways, it almost broke it.
Wow.
Yep. So where I'm going with all this is the reason it was down 200 horsepower with only 2 cylinders hurt is because those 2 hurt cylinders hurt all their neighbors. Because there's overlap.
Right. Yeah. It just disrupts the flow. It disrupts the household when you get two bad eggs, right?
Yes, it disrupts the household. Great way of saying it. All right. So long story short, the put up or shut up moment came last Tuesday, week from the day, where we put the engine back on the dyno. So same block, same heads, same manifold, same crank, same rods. So the rods and the pistons from before were CP pistons, Carrillo rods. So we actually sent the rods back to Carrillo. They checked them all out. They said they're still good. They were literally built in 1998. They had the serial number on them. They looked them up. They're like, we built these things in 1998. We checked them. They're good. Just put new rod bolts in them. Use them.
Nice.
All right. So they sent them back to us. We did new pistons. We went from a full round piston that was a 043, 1.5 millimeter, 3 millimeter ring setup. And we went to a 0.7 millimeter, 0.7 millimeter, 2 millimeter ring setup. We did the smallest lateral gas ports they could put in the pistons. And we put lateral gas ports in the top ring as well. Right. So we doubled it up. So,
and that 043 package was like top of the line back then.
Oh, that was state-of-the-art Cup. That was a state-of-the-art NASCAR Cup engine package. Was an 043, 3 millimeter back in the day. Now, as you can probably see from this thing, there they are. There's a little gas ports.
Mm-hmm.
So we did a gas ported 0.7 ring, which isn't even the thinnest thing out there now. So what they run in NASCAR today is actually a 0.5 millimeter. So we didn't even go to the nth degree on this thing. We didn't even change the compression height and go as crazy as we could, make the piston as light as we could. We kept the same rods, the same crank as we had before.
Right.
You know, same carb, same manifold.
What motor is this? What kind of motor is this?
Ford C3.
Okay.
So 358 cubic inches, Ford C3 head. So that was a mid 90s Ford engine. And we went to Billy Godbold at Comp Cams, and they did a new cam for us. We upgraded the lifters. It was a Bush motor. So back in the day, the Bush motors were rollers. So we went from the dog bone style lifters to a keyed lifter. So we John Cataly's at Morrell, we got their Black Mamba bushed keyed lifters and put those in there to take some weight out. We weren't trying to turn more RPM. We just wanted to make it smooth, right?
Right.
We had a little more lift with using the low shock cam design they have now that Comp's got. Change the springs. Interesting thing, by the way. Everybody's like, "Oh, the springs were dead. That's why it was so far down power." They were Iski tool room springs from the day. We checked all 16 springs. They were all within 5 pounds of the spec card.
Wow.
Even the ones that have been sitting open for 18 years.
Unbelievable.
So all those, I'm gonna call it myths about, you can't, take all the things. Really? I don't think so. I'm going to say no, based on what I just saw.
Right.
So I know that engine was stored. It wasn't stored in a perfect environment. It was just sitting there, right, on the floor of the shop for 18 years, and it didn't hurt a thing.
Wow.
So we did all this stuff, and we ran it last week. We made 780.
Woo!
300 horsepower.
Unbelievable.
Awesome.
That was on a temperature compensated dyno, right?
Yep. Yep. Got everything picked up. So we picked up basically about 100 from where it was brand new.
That's awesome.
Yeah. Pretty incredible. So it was neat to be able to put all the things we talk about all the time on the podcast and the different videos and stuff, and actually put it into practice. And we did it from what was state of the art 20 years ago.
Yeah.
It wasn't like it was a dog 20 years ago. It was a pretty good piece 20 years ago. And then, man, it was a big gain.
Awesome. Awesome. So yeah, the thin ring package is the way to go, it sounds like. And you've told us, the most friction, I mean, the biggest attribute to water temperature, oil temperature, it's all about this. It's these rings. The ring causing the friction.
This rubbing against the cylinder wall, which, by the way, this is a Top Fuel cylinder. We were honing for one of the Top Fuel teams at the Engine Performance Expo last week. And we were changing the surface finish on this. Because this ring running against this is the highest source of friction in the engine. But
the top ring is friction.
Top ring, the second ring, and the oil ring, all those things combined together, all that frictional drag is the number one source of friction in the engine.
Sure.
But one of the key parts about this, which is why we work with Greg to hone Dad's block, is you got to get the surface finish right in there. So you can probably see this a little bit, see some of that crosshatch angle. Boom, there it is. There's your crosshatch. You can see it. All those scratches that make that crosshatch come from the abrasive. It's like a piece of sandpaper, right? You got that rough little stone in there, and it's making that gouge in that surface. Well, we know that crosshatch angle, part of that's about making the ring rotate, the speed of that rotation. But the other part of that is it's what holds the oil. So the oil is there to do two jobs. It's one, there to lubricate the ring and the cylinder so they don't wear out. But most importantly, Oil is the gasket between the ring and the cylinder. So ring seal is about the piston holding the ring in the right location, right? The piston's all rocked over. Well, the ring's not going to contact the cylinder bore and it's not going to seal correctly. But I got to have a gasket between the ring and the piston and the cylinder wall. Oil is the gasket. If you think about it, anyone that's ever done a leak down test or compression test, you put a little bit of oil in that cylinder, what happens? It goes up. Why? It's the gasket that seals it. And when you put more fuel through the cylinder, you're going to need to have more oil on the cylinder to resist it being washed away. So, for example, this is a Darton liner that comes for the top fuel guys. From Darton, that thing has about a 50 RVK. So you just can use that term. And RVK is the valley. We're talking about these numbers. We're talking about, RPK. That's like the peak height. So if you think about this thing here is called a profilometer. And it's got a little diamond tip stylus right here. And it will trace across that cylinder just like a needle on a record player, for those people who are old enough to remember record players and needles and things like that. And it will trace that surface. And when it does that, so I can turn this thing on, it's going to leave that signature, right? And that signature from that, let me see, I can try to scan this cylinder while we're doing it. I'm going to let that thing go.
Now that's going to give us the RK, the RVK, and the RPK readouts?
Yes, it's going to do that. So most people do overlook it. They've been doing it the way they've been doing it forever. And one of the big problems is, okay, so you can probably see right here. Dang it. Okay, boom, there you go. You see that trace where you got those peaks and the valleys and all that right there. So this is measuring in micro inches. You got that right there? We can see it. So those those down lines or the valleys, that's what's going to hold the oil. So you think about these top fuel engines, they're putting so much liquid fuel into the cylinder, they need deeper valleys. So what we were trying to do here is take that valley that's from Darton around 50. Then we're trying to blow it up to 150.
Wow.
We got some of these guys like Jeremy Wagler, Drew at D&J, these guys that are doing these 3,000, 4,000 horsepower diesel engines. And what was happening with those guys, because they're putting they're running 300 PSI boost. 300. Insane. Well, think about it. The more boost you run, the more fuel you got to throw at it. Air fuel ratio.
Right.
They couldn't get off the dyno with an RVK of 50. They tried different pistons. They tried different ring materials and thicknesses. They were doing everything they could to get the thing to live, and they couldn't. We ran out of levers to pull in terms of materials and coatings and designs. And we were like, well, hang on. You're putting a lot of fuel in this thing. What's your surface finish? All right. They told me, said, well, we got to start trying to add valley. Let's start putting more oil there and let's see what happens. And literally these guys go from being barely able to get an engine off the dyno to running a full season, 30, 40 passes on the same engine, and the thing looks brand new.
Wow.
This is Black Death. This one's brand new. What's the difference? It's not the rings. It's not the pistons. It's the surface finish. By adding more valley to hold more oil. So in the old days, when everybody ran Molly rings, what was common was to use like a 280 grit abrasive to get within, say, 0.003 of size or 1,000th of size, depending upon what you're up to. And then you use like a 400, like a 220 or 400, and you crept up on it. But that last 1,000th you were doing, that was 400 or something like that. Yeah. Well, the problem is, this scale right here, that's plus minus 100 micro inches. So the entire surface texture is a 1/10 of a thousandths. 100 micro inches is 1/10 of a thousandths. So if you're taking out more than 2 thousandths on the dial bore gauge, whatever you finish with is what you got. You took all your valleys out. Well, the old Molly rings in the day were porous. They held oil. So it was forgiving. But you can't do a Molly ring when it's thin. Because the Molly is a coating that will actually sprayed on. It'll just flake off and fall off. And if you have any kind of detonation, you rattle it, it's gone, right? So that's one of the problems with that, is that you have to be able to make the ring thinner for more efficiency, but then you got to lose that porosity and then replace it with like a PVD style coating that doesn't have any porosity. Because of that, the cylinder wall now has to retain all the oil. So when you change the type of ring you're using, you really have to change how you hone it. I hear my cat. There's the cat. By the way, right on cue, right? So that's the biggest thing, is you have to change the hone when you change the rings to optimize what I call the ring seal soup. You know, how the piston, the ring, the oil, and the cylinder all work together. It's soup. It's not steak.
Okay. So then do you have specific like ranges that you would follow for a lot of the stock or super stock racers? The honing, the RVK, the RPK, the RK numbers that you follow? Like, could you tell everybody right now what, let's go with like a small block Chevy 350. I mean, it's probably the most commonly used engine in you know, stock and super stock.
Oh, no doubt about it. Actually, I'm going to pull up something, and I think I might be able to even show you something. All right, here it is.
Boom.
All right. So here's a trace, and you get all those little peaks and valleys I talked about. Then over here on the side, we've got another tool where we can actually see the crosshatch. So that's an actual USB microscope, this little guy right here, that lets you see that screen. It lets you see the crosshatch, and it will tell you what the crosshatch angle is. That's a whole nother discussion. But what you're trying to do is get a surface like this. So that surface, in terms of your RPK, RVK, and RK values, that you're looking for about a RVK of 50 to 60 is what you would really like to see. So that's the valley depth.
Okay.
Then the RK, you'd like it to be, say, 25 to 35.
All right.
Then you want
everybody writing this down?
Then you want the RPK to be 8 to 12.
8 to 12 on RPK.
Yep. In fact, if you look up here, that blue zone, that's your RVK, which first thing you're going to see is it's an average, right? The numbers are a numerical representation of the picture. What you're seeing right here is the actual trace. So the picture is what's real. The numbers are a numerical representation of the picture. So if you can actually see the picture, that's actually what's best. And so the red area here, that's your RPK. The area in between the red and the blue is the RK. And then the blue area is the RVK. So if you kind of notice that you say, okay, 8 to 12, then I'm going to want to be 25 to like 35. Then I want to be, 50 to 60. You think about those proportionally, you can kind of see that same proportion right here on that surface, because this is a good surface right here for a steel ring, what you guys are doing. Now that crosshatch angle is 45 degrees. For what most stock, super stock guys, you're probably going to be around 35 degrees, just for a higher performance application like that.
Excellent. That's why we brought you on here.
I'm happy to help, man.
Wonderful. Well, that's a nice piece of information. Everybody wrote that down, right? I know I did. So thank you for that, Lake.
I don't know. Happy to help.
The
What
honing
else we got
process,
today?
yeah, like you said, is crucial. Now, another thing that we got into oil
Mhm.
last time around, and you mentioned the oil analysis kit.
Yes.
Can you elaborate on that a little bit more? We can, we got a kit. I just got my kit from you. I can, after I run in the engine for the day or whatever, shut the engine off for a couple minutes, put some of this oil in there. I send it out to you guys. I send it out to whoever, and they tell me what's going on in there. Is that the way this works?
Right. So the great thing about engine oil is it travels all through your engine. Only place it doesn't go is through the intake and exhaust track, but pretty much everywhere else it gets to go. It picks up souvenirs as it travels through your engine. So by taking a sample of the used oil, you can tell what parts are wearing in your engine. A piston ring is going to be made out of iron, may have a CRN coating on it. Well, CRN is chromium nitride. So I can look for chromium in the oil to know if my piston ring face is wearing. If I have a bushed lifter that has a bronze bushing in it, I can look for the copper levels and know if I'm having lifter wear. I can look at my bearings as copper, tin, lead, tri-metal bearing, copper, tin, lead. I can look at those three as a combination and have an idea if I'm having bearing wear. You can look for contamination, like what's my percentage of fuel dilution? Am I running too rich? If I have more than 2% unburnt fuel in my oil, then either I'm running the wrong fuel in terms of the distillation curve for the temperature I run at, or I'm running too rich. You can tell that if there's a water, like in fact, we did all that work with Dad's engine last week, and the only disappointing yet exciting at the same time thing was when we took the oil samples from the break-in and all the dyno testing, we saw a little bit of water. Now, if you remember, I mentioned that Dad had ran that race back in Daytona 2004, which he won, but the engine was overheating a little bit. And he thought it was a radiator or something like that. Now he know, after refreshing it up and doing all that, there's a small leak somewhere in the engine, either in the heads or in the block. There's a small leak. So before we go back to the racetrack, we got to turn everything back down apart again and go find it. Now, here's the thing about it. If we didn't have the oil analysis, that engine would go in the car and go to the racetrack. And guess what? That same failure would happen again at the racetrack. And then it could cost us pistons, rods, crank. It costs us a lot.
Yeah.
But we're going to save ourselves a ton of headache later because we took those samples coming off the dyno. We were able to catch a problem before it turned catastrophic. Now, I don't want to have to go do all that work, but I'm glad that I know we need to do it.
Right.
I'd rather be knowledgeable and be proactive than get hurt and have, ignorance is bliss, but eventually that runs out.
Now this kit, we can get this kit from you guys at Total Seal?
Yep. Yeah, you can buy the kits from Total Seal. If you go to Total Seal's website, click on where the tools and accessories are. On the tools tab, there's a link to buy the kits from Speed Diagnostics. And essentially, yeah, you take that sample, you get that kit, open it up. There's going to be a sample bottle in there and a mailer and instructions. You just follow the instructions. You want to go online to the Speed Diagnostics website, fill out the submission form, which is going to tell us, okay, are you running leaded fuel, unleaded fuel? In your case, guys, it's going to be drag racing, what the engine is, what the viscosity of the oil is, and all that. Then we know that information about the application. The lab knows that information, so they know what test to run correctly. Then that sample goes in the mailer. You put it in the U.S. mail, shoots off to the lab. The lab gets it. They've got the submission form information, so they know it's coming to them. They know what test to run. They run the test. Then they give me back all the results. And I take your information, all the lab report, I put it all together and then send you an analysis of your application. And it's me giving you the results, not somebody else that doesn't know a wrist pin from a retainer that somebody like myself that has the experience, and all that's based on, I couldn't tell you what is good for a cat diesel running in a mining application because that's not my background. My background is racing engines.
Right.
So I can tell you what's good for a racing engine depending upon what fuel you're running and things like that.
That's awesome. Now, how many runs do you think the person should put on the oil before they drain that out? You wouldn't want to do it on brand new oil, right? Like with one run, would you say like 10 runs, or after a weekend of racing, take it out?
After a weekend of racing, you want to take samples at we'll call it your regular intervals of whatever the duty cycles and runtime are going to be. So if you go to a race and let's say you make, 8 or so passes over the course of a weekend, well, let's run a whole race weekend, bring it back, take a sample, send it off, and then you can build that trend line because it's building the trend. Like the one sample is going to tell you one piece of information. Where it gets really powerful is when you take samples on a regular basis.
Okay.
Then you get that trend analysis. In fact, every Formula One team has somebody like myself that goes to the racetrack with a portable lab setup. They take samples from every car every time it comes off the racetrack. They go run an hour practice session. They come back, they pull samples, they analyze it. And they look at the trend analysis because whether that car has, say, 10 laps on it or 40 laps on it, they can normalize that difference in time. Because as long as you know how much mileage is on it, then you can normalize it and look at the trend rate in terms of wear rate per mile or per pass or per lap or whatever the metrics want to be. You can set it up and then you can begin that trend analysis. Then you can look for any deviation. And that's the real key. It's a incredibly powerful tool. It's just something that, aviation, anyone that's ever ridden on a commercial airplane, there's been used oil analysis done. If you've ever ridden in a private plane, there's used oil analysis done. Submarines, aircraft carriers, nuclear power plants. All the stuff that we don't even think about in our daily lives that has lubricated equipment, they all do used oil analysis. We're just taking that technology and making it easy and accessible for the racing community.
Right. Now, the one concern I would have as a drag racer, we do not get our engine oils up to a high temperature to burn off condensation, things like that. That's the only thing that makes me nervous about it is I don't want to leave it in too long where that condensation might start forming. Sometimes you pull your valve covers off and you see that like milkshake substance on your valve train, things like that. So I don't want that to give you guys a false reading saying, hey, your heads could be leaking or your radiator, like something
that's the key, right? So that's where having the knowledge of drag racing is different than oval track racing, that you're going to expect it to be a little bit different. So, but I also say this too. Okay, what can you do to prevent that? Because just because it runs cold doesn't mean it has to have water in it. Maybe through the choice of oil you're doing or your warm-up routine or the fuel you're using, there may be something we can help you with to change up your program in order to reduce that, to mitigate so that you actually can go longer on your oil and make your engine run. Because really the goal of used oil analysis should be longer equipment life and better equipment performance. If you're interested in having your stuff last longer and run better, then used oil analysis is a tool you can use to achieve that objective. If you don't care about those things, then don't do it. Right. Because it's just because that's my whole goal.
I care.
My whole goal is to help someone go faster and be able to have more consistency and better longevity of their equipment. That's what it's all about.
Well, certain racers are all about we're all about the consistency. Some are about the horsepower, ragged edge. Some are about longevity. I don't have 3 engines on in the trailer with me, or in the garage. Like I need mine to last and perform efficiently and optimally. Which brings me to my next point. talking about drag engines not really getting up to temperature. Engine temperature. I mean, you stressed it so much in the last episode that we did together. You got to record your engine temperature. We have to know what these engines are operating at.
Yep.
In order to, I mean, pick a viscosity level to run an optimal, I guess, oil pressure varies. You fire the engine up cold and warm it up, you're going to have different oil pressure than, say, driving back after a run on a hot July day. So things change there. So that's one thing that I definitely took from the last lesson. I put a gauge in my car to find out exactly what this engine oil temperature is running. And mainly for me, I'm like 150 degrees is what I'm coming out to.
That's good.
I mean, a pro stocker that they can tow up there is probably about 100 degrees, but in stock and super stock, mandatory, you have to drive your car up to the staging lanes and drive it back from a run. There's really no towing allowed. So we get up a little bit higher, but that helped me, okay, I kind of used the calculators online to say, what actual viscosity am I running at 150 degrees when I punched in my oil specs and stuff. So definitely something that I learned from there. But like, I want to get into oil pressure. That's the one thing that we kind of didn't get into last time. Can you speak on oil pressure? Is there a certain pressure that you go for with certain combinations? I know I ran an overhead cam motor. I was driving for somebody and we were at 80 pounds of oil pressure. My small block Ford, 289, we're at about 50 pounds of oil pressure. So like high volume pumps, are you into that? Like what?
No, I hate high volume pumps. Okay. So yeah, the idea when people say they have a high pressure pump, okay, there's no such thing as a high pressure pump necessarily. Well, it can give higher pressure because it basically is changing the pressure relief valve, and it may be a higher volume pump. Oil pumps do not make pressure. They only make flow. Is the resistance to the oil flow through the oiling system that generates pressure.
So you got to remember that. And such.
Yep, all the leaks, right? So obviously the oil viscosity is part of that. It's how it flows. So really what you're trying to do is you want enough oil pressure to supply, to feed all the things throughout the engine, to reach the top of the engine, things like that, and to feed into the bearings and all that. But once you have that, really everything beyond that is waste. The old, Smokey Unique thing of, you need 10 pounds oil pressure for every 1,000 RPM. Well, if that was the case, when the Formula One engines were turning 20,000 RPM, they had 200 pounds oil pressure. I can tell you they didn't. In NASCAR, when we were turning 10,000 RPM, we'd had 100. And I can tell you we didn't. I will say that depending upon the compression ratio, because that's going to make a big difference in how much load is on that rod bearing. If that somewhere between 40 to 60 PSI is a pretty good range. The lower the compression, the lower that number can be. The higher the compression, the higher that number needs to be. Plate racing in the early 2000s, that was 20 years ago, we ran about 16 pounds wide open throttle.
Wow.
Now that was trying to squeeze every last horsepower out of it. GM had done some studies, and there's some SAE white papers and all that said they could run an engine on about 8 pounds oil pressure. That's really low.
My light would be coming on.
Yeah.
Now I have a shut off in my stocker, the fuel injected car, where if it drops to below 10, it'll shut the car off. But so I've lowered that a little bit because on a hot day after a run and I went to a thinner oil this past year, if at an idle, that thing will be down here. You give it some throttle to drive back, it's
exactly. Yeah. So I think the rule that GM came up with was 6.5 pounds of oil pressure per 1,000 RPM is the minimum spec, right? So if the engine's idling at 1,500 RPM, then it'd be about a little over 10 pounds or so. But if you kind of play that out, say we'll just round it down to six. So on a 7,000 RPM engine, that's 42 pounds of oil pressure, which again falls into a lot of the stuff we've seen, that if you lower compression engine, you could run 40 pounds and be just fine. So oil pressure is one of those things where more isn't necessarily better. And if you go too much, you're just leaving efficiency on the table.
Right. And if you go too low,
there's a problem.
You could sacrifice lubrication and all kinds of other things.
Yeah, you definitely, under wide open throttle at operating temperature, you really don't want to be less than 40 PSI. I like to see somewhere 50 to 60. To me, is a good place to be. We were dynoing Dad's engine. We put in the 0W16, and at 200 degrees oil temperature, that thing was making right around 45 pounds of oil pressure, wide open throttle, and that was on a fairly loose clearance. I knew what we were doing. I was like, it'll be all right for what we're up to. And oil analysis didn't show anything on the bearings that was bad, so we knew we were good in the bearings. With that, so we were fine. But to go to the racetrack, I wouldn't go to the racetrack with the 016 in it. Based on what we saw with the dyno now, I'll go with the 520 instead. Just a little bit thicker is all we needed, because that would probably push that from 45 to 50, and 50 we're going to be good.
Okay. So back to that oil analysis kit then. If I send one in, I'm using 1030 or whatever. Everything seems fine. You don't see any wear and tear anywhere. And I know that I have about 55 to 60 pounds of oil pressure every time I go down the track. Is that an indication that, hey, maybe we could go from the 1030, let's try like a 520? And
you could, right? Looking, when we measure the used viscosity, then we'll be able to see, right? Because there's the viscosity of the oil new, but then once you've run it through the engine, it's had a chance to shear and you get fuel dilution and all that, then we'll see what your operating viscosity really is. Then we can say, okay, is there any room to move down or not?
Okay. Does the operating viscosity usually reduce or increase?
Usually reduces. Usually what we'll see is that once the oil goes through the engine and is subjected to shear, it typically comes back thinner.
Okay. Got it. All right. Well, that's good to know.
Yeah. And the more fuel dilution you have, the lower the viscosity goes. In fact, when doing some work at Gibbs, they started doing this desert off-road truck racing stuff. And, the Baja 1000 and things like that. And it's all built aluminum block, and they race through the night and all this. Well, they were getting so much fuel dilution running this, high octane, high compression race fuel. When it would get down into the 30s and 40s at night on those desert races, the fuel was so cold, the fuel dilution would go so high that the viscosity from a 10W30 would drop down into the 20 range, and you saw the bearing metals increase. So we ended up having to go to a 15W40 oil to protect the bearings when they ran, not when it was hot, but when it was too cold.
And that goes against everything that we believe. We think, oh, it's cold out, we need to switch to a thinner oil.
Right. Well, that's why, again, without the oil analysis, you would have never known that.
Right.
And you could have potentially caused a problem. And what would happen is you said, oh, that oil is too thin. That's what got us in trouble. When it wasn't the oil's fault at all, it was the fuel dilution.
Yep. Again, good to know, because we all fatten our, mixture up when it's cold out. I mean, Atco in April, I don't know if you've ever been there, but it's just, you can go fast there, and it's the weather's sea level or below sea level.
Nice.
But to go further into the oil, and now you did talk about this in the last episode, but I have, a bunch of new listeners now that don't race stock and super stock. Conventional versus synthetic oil, it sounded like you really preferred a semi-synthetic blend for a lot of our race engines. Can you speak to that a little bit for the stock and super stock engines?
Yeah, so the semi-synthetic stuff is really nice. So, and the reason why is, without getting too crazy technical on all the details because I could spend another hour going over this by
Well, you can
itself.
get into the Strybeck curve if you want. Come on, we're here.
All right, nice. Look, he's paying attention. I like it. Look at him doing his homework. So a conventional base oil is, that's refined from crude oil. It's going to have a little more internal resistance, so it's not going to be as low friction as they say a full synthetic will be. But it has what's called a high pressure viscosity coefficient, so that as you apply really high levels of contact pressure, not oil pressure, but contact pressure, the oil actually will get thicker in that contact area. The downside is it can become almost solid, so there's no flow now. So now it can overheat parts and you're not getting the cooling for those areas, so that can become an issue. With the full synthetic, is a very low pressure viscosity coefficient, which means under that high contact load, it just gets pushed right out. So it's going to rely on the additive package, the ZDP and the things in the oil, to do all the protection at that point. With a blend, a semi-synthetic, you're kind of getting the best of both worlds. You're getting some of the lower friction characteristics of the synthetic blended in, but you've got this pressure viscosity coefficient that's kind of in between. It's not down here. It's not up here. It's kind of right down the middle. So it works out really well. The driven GP1 line of products is a semi-synthetic that's where the conventional oil is the Pennsylvania crude, the old Kendall type stuff. That's same refinery, actually. They did the original Kendall oil is who does the driven GP1. So it's got that great Pennsylvania crude, but then you're blending in the synthetic with it to give it that middle ground. And the results we've seen from that have been phenomenal. And of course, with the oil analysis stuff, that's where we get to see a lot of different oils from a lot of different applications. And that semi-synthetic comes back looking really good a lot of times.
That blend, the GP1 especially, do you know what the percentage of synthetic is in that blend?
Well, it varies based on the viscosity. So like a 2050, the thickener part is the mineral based, because the conventional mineral oil tends to be thicker than the synthetic part of the base. So the 2050, it'll be a lot lower percentage synthetic compared to the 520. The 520 is going to be way more synthetic than the 2050 because you're using more of that low viscosity base oil that's synthetic.
Right. All right. So I do run a semi-synthetic in the super stock car. I run full synthetic in the stocker, but that's good to know. Now, I know you did recommend that BR30 for the break-in oil.
Oh, yeah, absolutely. You definitely want to use break-in oil.
Yeah, cool routine for breaking in engines. You want to speak to that real quick for everybody? What you recommend, how many passes you would like people to run the break-in?
Sure.
Or dyno pulls.
Well, yeah, if you have a dyno, and we actually have a couple of things there on the Total Seal YouTube channel. We have two different videos. One is for the break-in of an engine on the dyno. Then we also have one without the dyno that will kind of go through the whole process. The key is this: you don't want to idle the engine, and you do not want to, or you say you can't technically break in piston rings on a run-in stand, because a run-in stand can't apply load. You could break in a flat tappet cam on a run-in stand. You can check for leaks on a run-in stand, but you can't break in piston rings because piston rings need cylinder pressure. And there's very little cylinder pressure without any load. And run-in stands can't apply load. So you need to have the load. You need to make passes. And it's really important to have a break-in oil that is low in detergent, no friction modifiers. That's the key. That's what makes the Gibbs, the driven break-in oil, the BR30, so good. Is it's low detergent, higher zinc, no friction modifiers. That's the special part of it. So it lets the ring break in to that cylinder wall. Because really, it's not so much the ring that's wearing in, it's the cylinder wall that's wearing in. The ring really doesn't change that much. If you looked at it under a microscope, it's the cylinder that's going to change. In fact, if you want me to, I can even show you a picture of what one of those looks like. And so as you can see, this top part here is the unrun part of the cylinder. And this part down here is the run part of the cylinder. So we've taken a cylinder and we've measured above and below ring travel. And you can see the difference in what that cylinder looks like. Under a microscope, the ring face really doesn't look all that different. But you can see over here where the unrun area is, how those peaks are still peaky, but over here, they're rounded off. That's the broken in part versus the unrun part. I mean, isn't that cool? Where you can see it?
That's amazing. I need to, where do we get one of these tools?
It's really neat when you can see it. You're not having to worry about numbers and all that. It's like, oh, this part isn't broken in. That part is broken in. Okay, got it. I see everything now.
Very informative. I like it. Thanks a lot, Lake.
Pictures are good, right? It's so much better to show pictures than to talk about it.
Absolutely. Now, Lake, well, we thank you for joining us today. It's been an hour already. Can't believe it. That flew by. But
it goes by fast, doesn't it?
I got to have you on for part 3 someday.
I'm in.
I'm
always willing to come back. And we only scratch the surface. We hardly, no pun intended there, by the way, scratching the surface. Talking about honing. But there's so much more we could talk about and show, and just a lot of neat things that there's a lot of opportunities to be able to improve efficiency and go faster.
Will you guys be doing track seminars again this year at National?
Yes. So Gainesville, Gator Nationals, we are doing the first Trackside Tech Talk in Gainesville at the Gator Nats, right there next to Matt Harper's Pro Stock Car. We'll be there Friday and Saturday.
Friday and Saturday. All right. I will be at the Gator Nationals. I am driving a stock eliminator car down there, so I look forward to seeing you. And I mean, hopefully I'm still racing on Saturday, but if not, I'll definitely be at the ring seminar. All right, Lake. Thanks a lot for joining us. We appreciate it. Take care, everybody. Thanks for watching.